am Nelsie Rugi-Pitaros, BSIT student from G.H. Riley State College. Today we will talk about mathematical reasoning and their kinds of reasoning. What is mathematical reasoning? In mathematics, reasoning involves drawing logical conclusion based on evidence or stated assumptions. It involves the use of cognitive thinking, which has a logical approach. Mathematical reasoning helps the student identify the solution and understand if it makes sense. Like for example, Earth is a planet. This statement can be considered as a math reasoning statement because it is true. It is a simple statement because it cannot be broken down into further simple statements. Kinds of reasoning. First, we have intuition. Intuition is a process that gives us ability to know something directly without analytic reasoning. It is that kind of mental ability by which one reaches a conclusion by more gazing. Like for example, guessing someone knocking your door. Number 2 is analogy. An analogy is something that shows how two things are alike, but with the ultimate goal of making a point about this comparison. An inference conclusion on the assumption that if two things are alike in some aspect, they must be like in others. Like for example, life is like a box of chocolates. You never know what you're gonna get. You can use metaphors and similar when creating an analogy. Another example, Sylvia and Veronica are sisters. Sylvia is intelligent, therefore, Veronica must also be intelligent. Number 3, inductive reasoning or inductive logic. It is a method of reasoning in which a body of observation is synthesized to come up with a general principle. It is a type of reasoning which concludes on the basis of a limited number of instances that something is always have. They must not be misled into believing that something is always true because we observe it being true for a number of instances. Like for example, in the summer, there are ducks on our pond. Therefore, summer will bring ducks to our pond. Another example, I see fireflies in the backyard every summer. That will be the data.
Hello, My name is Ram and welcome to another video of Matuklasan. Reasoning is the action that we do whenever we want to think or say something in a logical or sensible way. This is like our go-to defense mechanism when we want to justify our actions and statements to other people. Reasoning is often a highlighted topic in various fields like philosophy, science, language, mathematics, and art, and is normally considered as one of our distinguishing abilities as a human. In logic, reasoning is the drawing of inferences or conclusions from known or assumed facts. The two major types of reasoning are deductive and inductive. These refer to the process by which someone creates a conclusion as well as how they believe their conclusion to be true. Deductive reasoning is the process of reaching a conclusion by applying general ideas called premises. This concept is often expressed visually using a funnel that narrows a general idea into a specific conclusion. Recognized rules, laws, theories, and other widely accepted truths are used to prove that a conclusion is right. The most common form of deductive reasoning is the syllogism, where two premises that share some ideas support a conclusion. In symbols, A implies B, B implies C, therefore A implies C, where A, B, and C's are propositions or the general ideas that we are referring to. This one is also similar to transitive property of equality, where if we have A plus B or A equals B as our premise and B equals C is another premise, then A equals C because both are equal to B. For example, all men are mortal. Ram is a man. Therefore, Ram is mortal. In symbols, let this B implies C. And this one be A implies B. So we can see here that B are the same. So A implies C. Another example, all even numbers are divisible by 2. 22 is even. Since we have the same idea here, therefore 22 is divisible by 2. Next, Marvel Comics characters are fictional. Iron Man is a Marvel Comics character. So we have here comics character as the same idea. So therefore, Iron Man is a fictional character. Citrus fruits are rich in vitamin C. Orange is a citrus fruit. Therefore, an orange is rich in vitamin C. Now, how about this example? All musical instruments make sounds. Jeepneys make sounds. Therefore, jeepneys are musical instruments. Teka. All musical instruments make sounds. This is true. This is a true premise. Jeepneys make sounds. This is also a true premise. But jeepneys are not musical instruments, so this is false. Therefore, this is not a valid deductive reasoning. Always remember that we use premises to prove the conclusion is true and not to justify it. Deductive reasoning is meant to demonstrate that the conclusion is absolutely true based on the logic of the premises. Inductive reasoning, on the other hand, is the process of reaching a general conclusion by examining specific observations. So, a few particular premises create a pattern which gives way to a general conclusion that is likely true. This is commonly shown using a triangle that starts at the narrow premises and expands into a broader conclusion. Unlike deductive reasoning, inductive reasoning has no basic standard format when we use it. So as long as we are finding a conclusion that is most likely to fit the premises, then we can make predictions, create generalization, and analyze cause and effect. Keep in mind that in deductive reasoning, premises are used to prove a conclusion, while premises in inductive reasoning are used to predict a conclusion. meaning we don't create a definite answer, but we are trying to show that the conclusion is the most probable one given the premises. For example, yesterday morning, Isa went jogging. This morning, she jogged again. Therefore, Isa will probably jog tomorrow morning. This conclusion is not definite, but basing on the morning routine of Isa, there is a high chance that she will jog tomorrow morning, right? Now, what if we are asked to find the next figure in this pattern? The first figure is a square. In the second figure, a second square was constructed inside of the first square, wherein the vertices of this new square are on the midpoints of the sides of the first square. Following the same pattern, and by using inductive reasoning, it's possible that the next pattern is this one. An inductive argument is either considered weak or strong based on whether its conclusion is a probable explanation for the premises. Let's compare these inductive arguments. On the left, the two statements are likely true on their own, but the first premise does not predict the second to be true, because I probably know what's funny for my friends, but some may find it corny, right? On the right, we can see that these numbers are all multiples of 3 in ascending order. So it is logical to say that the next term after 15 is 18, because the premises identify a pattern. Thus, the reasoning on the left is weak while the right is strong. Now let's try determining the kind of reasoning used in each argument. For number 1, the teacher used Google Classroom in the last few classes. So based on this pattern, we can say that the teacher will use Google Classroom tomorrow. But this is not definite, right? So this is inductive reasoning. Number 2, all licensed drivers are 17 years old and above. Marcus has a driver's license. Therefore, Marcus is at least 17 years old. Syllogism was used and we have a true conclusion. So therefore, this is deductive reasoning. Next, all spiders have 8 legs. Black widows are spiders. Thus, black widows have 8 legs. Just like in number 2, this is deductive reasoning. Number 4, my father has black hair. My brother has a black hair. So based from these two premises and pattern that we can see, therefore everyone I am related to has a black hair. But this is just a probable conclusion. So this is inductive reasoning. Number 5, the Game of Thrones TV series was a worldwide success. Therefore, any sequel for the series will probably be successful. This is inductive reasoning. And that's all for this video. If you want more video lessons in math in the modern world, please check my playlist in the description below. And please like, share, and subscribe for your updates. Thank you for listening.
Good day. By the way, my name is Edward M. Rabi, a BSET student in JETS Real Estate College. So, quantifier statement. An essential quantifier state that a set contains at least one element. Something interesting happens when we negate or state the opposite of a quantified statement. A quantified statement is one that says something about all, some, or none of object in a collection. Example, all students in college are taking history. Next, some students are taking mathematics. No students are taking both mathematics and history. Equivalent statement. Equivalent statements are statements that are written differently but hold in the same logical equivalent. In any language, there are many ways to say something. The different linguistic construction of a statement are considered equivalent. Example, If state if statement can be proved by each other. A dog is an animal. A pet is an animal your own. So owning a dog would be owning a pet. Therefore, if Chris owning a dog, then he own a pet. If Chris doesn't own a pet, then he doesn't own a dog. Another example, all students in college are taking history. Every students in college are taking history. Some students are taking mathematics. At least one of student is taking mathematics. Negating quantified statement. Sometimes in mathematics is important to determine what the opposite of a given mathematics statement is. This is usually referred to as negating a statement. One thing to keep in mind is that if statement is true, then its negation is false. And if statement is false, then its negation is true. The negation of a statement about all object is not all. Not all can often be expressed, some are not. Example, fact. None is the opposite of at least one. For example, the negation of some dogs are paddles is no dogs are paddles. Another example, all students in college are taking Filipino. Some students in college are not taking Filipino. Compound statement. A compound statement is a sentence that consists of two or more statements separately by logical connector. Simple statement can be connected with the either or if, then or if and only if. This more complicated statement called compound. Example, it is no snowing and I wish that I were out of doors, but I made the mistake of signing up this course. Another example, Miami is a city, Florida is a statement. Atlanta is a city in Florida is a false statement. Either Miami is a city in Florida or Atlanta is a city in Florida is a compound statement. Is that true? Miami is the city in Florida and Atlanta is a city in Florida is a compound statement that is true. So that's all and thank you.
Now let's discuss quantified statements. Quantified statements are statements that has quantifiers. So the quantifiers are the words all, some, and no or none. These statements here are statements containing a quantifier. All poets are writers. So this one is quantifier. Another example, some people are bigots. No math books have pictures. Some students do not work hard. These statements here are examples of quantified statements. In the following table here, we can see the ways or equivalent ways of expressing quantified statements. For example, we have the statement all are B. An equivalent way to express the statement is there are no A that are not B. Examples using two equivalent quantified statements, all poets are writers. Then we would just say there are no poets that are not writers. So A here is poets, B is writers, and then when you say there are no poets that are not writers. Okay, so let's consider the statement some A are B. Take note, this A and B here might be words or statements. An equivalent expression for this statement is, there exists at least one A that is a B. If we consider the statement, some people are bigots, the equivalent for this statement is, at least one person is a bigot. The statement, no A or B. An equivalent way to express this statement is, all A are not B. So an example to this one, an example of no A or B in this format is this statement, no common colds are fatal. Now, equivalently, we could say this statement as, all common colds are not fatal. Then we have this statement, some A are not B. So this statement, some A are not B, is equivalent to, not all are B. This statement, some students do not work hard, is an example of a statement in this format, some A are not B. Some students do not work hard. And equivalent to that statement is, not all students work hard. From the previous example, we could easily see the negation of the quantified statements. When you say, all are B, if you negate this, the negation of all is some. So to negate this one, all becomes some. So all A becomes some A, and R become are not B. So all A are B, when you negate that, is some A are not B. And then this is equivalent to, not all A are B. Again, as I mentioned, when you say some, the negation of some is no. So some A are B. When you negate that, you will have no A are B. The negation is, all A are not B. I want you to take note of the relationship. Again, the negation of all is some, and the negation of some is no. Now, here are some examples of quantified statements. This is the statement, and we'll look at the negation. So, we can also represent our statement using Venn diagram. So, when our statement is, all writers are poets, meaning if you're a writer, then you are a poet. So, you can represent it using this Venn diagram here, wherein a writer is a subset, a proper subset for poets. When you negate this, the negation of all is some. So when you negate that, that becomes this statement here. Some writers are not poets. Or if you want to see the Venn diagram for this statement, you will actually be looking at this Venn diagram here, wherein this one is a poet and a writer. And this region here is a region then for the negation, where you have some writers are not poets. Again, the negation of all is some, and the negation of are is are not. Take a look at this statement here. We have the statement, some canaries weigh 50 pounds. As I mentioned, the negation of some is none or no. So when you negate some canaries weigh 50 pounds, this will become, no canary weighs 50 pounds. This statement here can be represented using this Venn diagram, and we're actually referring to this region here. Some canaries weigh 50 pounds. So you have canaries and then 50 pounds. Now to negate this means this region should not exist. So to do that, you just have to separate these two sets here. You have canaries and then 50-pound objects with no intersection. That is the negation. This region here, everything is inside poet. When you negate that, you just say, not everything in here is inside here. So that's how you ended up with this representation here. You just have to take note that the negation of all is some, and the negation of are is are not. Now let's take a look at an example of how we can negate a quantified statement. Consider this statement here. The mechanic told me all piston rings were replaced. I later learned that the mechanic never tells the truth. What can I conclude? So to do this, let's try negating the statement all piston rings were replaced. We begin by the mechanic statement, which is all piston rings were replaced. If you remember, the negation for all is some, and the negation for were would be were not. So because the mechanic never tells the truth, I can conclude that the truth is the negation of what I was told. Again, the negation of all are B is some A or not B. So therefore, the negation of this statement here is that some piston rings were not replaced. And I can also correctly conclude that at least one piston ring was not replaced, because this statement here is equivalent to this statement. The equivalent of some A or not B is at least one A is not B.
Good day, sir. I am Kevin Iela, one of the reporter from Group 2, which is reporting the set theory or the review on set theory. Set theory is the mathematical theory of well-determined collections called sets of objects that are called members or elements of the set. The actions of the set theory imply the existence of a set theoretic universe so that all mathematical objects can be constructed as sets.
Welcome to Discrete Mathematics. Let's start with set theory, which is a very fundamental notion in the entirety of mathematics. So what is a set? A set is a collection of objects called elements. And this is very vague because we can have a set about anything we want. And usually we talk about sets by drawing these little circles. So for instance, if I want a set of, let's say, the numbers 1, 2, and 3, I can draw a circle and I can put the numbers 1, 2, and 3 in there, and that is a set containing the numbers 1, 2, and 3. And we can write this formally in curly braces and writing all of the elements inside. So in this case, our set contains 1, 2, and 3, and we can give this a label and maybe call this A. So these are all different ways of representing the same thing. A is the set 1, 2, and 3, which looks like a circle containing elements 1, 2, and 3. Of course, this is just visual, and this notation in curly braces is called a list notation because you're listing them all. Now, sets can be finite or they can be infinite. So we can have a set A containing all the numbers between 1 and 9, or we could have the set of positive integers that go from 1 all the way up to infinity. And in this case, this is an infinite set. So these ... dots mean that there's an implied pattern that just goes on forever. So here, z plus, if we have 1, 2, 3, 4, and we put ... we mean that it goes 5, 6, 7, 8, 9, 10, so on and so forth. So those are really the fundamental notions of sets. Now there's some additional points to these sets. and that is that repeated elements are only listed once. So if we have a set A, B, A, C, B, A, even though A is repeated 3 times, we only write it once. B is repeated twice, we only write it once, and C is repeated once. So this set ABACBA is the same set as ABC, and they would both be drawn as circles with some element A, some element B, and some element C. In other words, we don't care about the amount of numbers of these things in there. We don't care if there's 3 A's, we don't care if there's 2 B's. We just want to know what's inside our circle. There's also no order in a set. And in a diagram, this is easy to see because there's no order in a circular diagram. But essentially, the set 3, 2, 1 is the same thing as the set 1, 2, 3. And that's also the same thing as the set 2, 1, 3, so on and so forth. There's no order to these sets. So those are 2 pretty important parts. Usually on an exam, you might be given a set that has repeated elements, and they might ask you, how big is this set? How many things are in it? And if you're not sure about repeated elements, then you might get the wrong answer. There's a few common sets that we should talk about. One of them is the natural numbers. The first time I made this video, there's some controversy. And there's still some controversy. But there's 2 ways to do the natural numbers. One of them is to start with 0, do 1, 2, 3, all the way up, forever and ever. Another group of mathematicians starts the natural numbers with 1, 2, 3, so on and so forth. I'm going to refer to the natural numbers, starting with 1, as the positive integers. And when I talk about natural numbers anywhere else, I will usually mean including 0, but I may be more specific about it, so I will specify whether it includes 0 or not. But typically with 1, 2, 3, so on and so forth, I'll use Z+. The integers are a set of numbers which are either positive or negative, and they're whole numbers. So all the way from negative infinity, -2, -1, 0, 1, 2, all the way to positive infinity. So that is Z. That's a very important notion, which we use a lot in discrete math. And then rational numbers. Oh, these are kind of hard to list. So I'm going to cheat a little bit for now, and I'm going to say, well, we have like 1 over 1, 1 over 2, 1 over 3, 2 over 3, so on and so forth. And in a few slides, we'll figure out a better way to write this. So, of course, rational numbers are any numbers you can write as a fraction. So, elements and cardinality. Now we know what sets are. Now we know some additional pointers about sets. We know some common sets. But we want to be able to talk about the things in those sets and how big those sets are. So I have C, and I have a set containing yellow, blue, and red. So these are the primary colors. In fact, sets don't have to be all mathematics. They can be words too and have meaning in the real world. So I want to say something like yellow is an element of C. And this means that yellow is inside of our set C. Now, how do we write this? Well, we have an element yellow, and we want to say it's part of a set C. So in order to write this in notation, we use this epsilon. So yellow is in the set C. What about saying green is not in the set C? So I want to say green is not in here. In fact, we don't see it in the set C. So what do we do to say green is not in C? Well, we use the set membership symbol, and we just put a line through it to mean green is not in our set C. How do we talk about the size of this? How do we say the size of C is 3? Which means the amount of things in C is 3. There are 3 different elements in C. Well, we just draw these absolute value bars around it. So we say that the absolute value, or the size of C, is equal to 3. And that says that the cardinality of C is 3. So now we can talk about whether things are in our sets and how many things are in our sets. Now there's one particularly interesting set that contains nothing in it. This is called the empty set, and this is written with this symbol. And if I wanted to write it in the set notation with curly braces, it would look like this. It has a left curly brace, a right curly brace, and then there's nothing inside of it because it's empty. So what's the size of this set? Well, there's nothing in it. So the size of it is 0. And there's only one set that has a size of 0, and that is the empty set. So here's a question. And I'm throwing this right at you right away because this trips people up all the time. What is the size of the set containing the empty set? So I'm asking, if I have a set containing the empty set, what's the size of that set? Well, this empty set is an element of the larger set. So the size of the set containing the empty set is 1, because this set itself, this big set, has one element. It has an empty set as an element. So sets can have sets as elements. We'll see another example later, but typically I like to look where the commas are. So if there's like a big set, then a comma, then another big set, and that's all that's in the set, then there'd be 2 elements. In this case, we have these empty braces, but there's something inside of it. So therefore, there's an element in that set. This is different, of course, than the size of the set containing nothing. This would be 0. So we can see the contrast between these two sets. This is the empty set on the right, while this is a set containing the empty set on the left. The left one has a size of 1, the right one has a size of 0, and we can see the differences visually. Okay, so that's the empty set. There'll be more questions about the empty set when we get to the subset video, so more tricky stuff will happen there. The next thing we should talk about is set builder notation. So before I introduced the rational numbers, and I said, oh, it's 1 over 1, 1 over 2, 1 over 3, 2 over 3, so on and so forth, there's got to be a better way of representing this entire set. And this is set builder notation, or we can call it maybe predicate notation, where we define elements as variables. So for instance, I can say this is the set containing elements that are of the form m over n, such that, so this straight bar means such that, and now I'm going to give a rule. So the left is like the form that it takes, and on the right side, we're going to give it a rule. We're going to say that m and n have to be integers, and also n has to not be 0, so that way we're not dividing by 0. And this expresses the entire set of rational numbers. I'm saying, look, take any 2 integers, m and n, we can put m on top of n, and as long as n isn't 0, it's going to be in that set. So I'll do another example with even integers. So we can write all the way to negative infinity, negative 4, negative 2, 0, 2, and 4, so on and so forth to infinity. Or we could do this in set builder notation. So we could say this is the set of 2n such that n is an integer. So what this means is we take an integer n, so let's say we take 1, then in our set we add 2 times that integer, so 2 times 1, so we add 2. Let's say we take 2, then we take 2 times 2 and put in our set 4. Let's say we take negative 1, then we take negative 1 times 2, and then we get negative 2 in our set as well. And this just goes on forever. So for every n that is an integer, we add 2n to our set. And that gives us the set of even integers. So here's a more linguistic example, so something we can apply in the real world to see how this notation works. I have a desk. And on this desk, I have a drink, I have a laptop, and I have a microphone. And there's some other things on my desk that I could list, but let's just say my desk only has these 3 things. Now, this is one way I can talk about things. I can say I got this drink, this laptop, and this microphone on my desk. Or I could write this in set builder notation if I might have a lot more things, or maybe I want to be vague, or maybe I'm not entirely sure what's on my desk, but I know there's things on my desk. So I could rewrite this as the set of x So this is a variable x. And what's the condition for x? X is on my desk. Yeah, so this is kind of cheating, right? But they're the same sets. So the first one I'm listing all these items individually. The second one I'm saying, look, it's the set of variables x, and whatever x is, it just happens to be on my desk. So everything that's on my desk, it's just going to shove it in as x, and it's going to build a set with it. So that's the set builder notation. And of course, mathematically, we do this very formally with, of course, numbers and formulas and notation. While, of course, if you do a linguistics example with words, it's much more wordy, it's much more flexible, much more floaty, but they both convey the same meaning. So if you didn't quite understand the mathematic example, then hopefully you'll be able to translate this desk example back into the mathematics after, while maybe understanding this at a more fundamental level. So here I have some exercises. And these all refer to the first two refer to the set D, and the third one is completely different. Try them yourself, and if not, well, I'll give you the answers now. So list the elements of D. D is the set of x in positive integers such that x is less than 6. So I'm going to take all x less than 6 and add them to the set if it's a positive integer. So this means that I can have 1, because 1 is a positive integer and it's less than 6. Let's do this in a different color. 2, 3, 4, and 5. Can I add 6? I can't add 6 because x is not less than 6. Can I add 0? Well, I can't add 0 because I specifically want the x's that are in positive integers, and 0 is not a positive integer. Okay, what's the cardinality of D then? Well, this is easier because I've already written out all the elements in my set. So I see there's 5 things there. So I can say the cardinality of D is equal to 5 because it contains the numbers 1, 2, 3, 4, and 5. Now here's another question, and this is what I alluded to before. What is the cardinality of the set containing the empty set and the set AB? Okay, so how many elements are in the set? And when we look at sets, it's kind of like looking into a box and saying, well, what can I see? I see an empty set, and I see another set. So really what I see inside this box, if I were to draw this out, is a box containing nothing and a box containing A and B. So the stuff inside of these boxes, essentially with a cardinality question, these things are invisible. We can't see what's going on. So the question is, how many things do we see inside that set? What is the size? How many elements are in that set, that big box? And the answer to this is 2. And this is why I said look at the commas here. So we have an empty set, which is the first thing. Then we have a comma. Then we have this other entire set. So there's 2 things we can see. Now, how does this differ from, let's say, if we have a set containing the empty set, the set containing A, and then the set containing B? Well, this is different, of course. So in this example, if I were to draw this, we have a box containing nothing in it. We have a box with A in it, and then we have another box with B in it. So how many elements do we see? Well, we can't see inside these boxes, but if we just open our box and take a look, we'll see 3 other boxes. So in other words, the size of this would be 3. One more example. Let's say we took away one of these. So now I have something that looks like this. I have the empty set, I have the element A, and I have a set containing B. Once again, there are 3 elements that we can see. We can see this box containing something, we can see the element A, and then we can see this box containing something else, which happens to be B. So once again, this cardinality is equal to 3. So that is it for the Introduction to Set Theory video. If you have any questions, please leave them in the comments below, and I will do my best to answer them.
The father of set theory is the George Ferdinand Ludwig Philipp Cantor. George Cantor is in full George Ferdinand Ludwig Philipp Cantor, born on March 3, 1845 at St. Petersburg, Russia, died on January 6, 1918 in Halle, Germany. A German mathematician who founded set theory and introduced the mathematically meaningful concept of transfinite numbers indefinitely large but distinct from one another. So a set is a well-defined finite or infinite collections of things, objects, or ideas. Order has no significance and multiplicity is generally also ignored. Members of a set are members of a sets are often referred to as elements, and notations is used to denote them. Example: the items you wear. This would include shoes, socks, hat, shirt, pants, and so on. Also, the types of fingers would include index, middle, ring, or pinky. The properties of sets. Finite and infinite sets. The finite sets are used that have a finite number of members, and if the elements of a finite sets are listed one from another, the process will eventually run out of elements to list. An infinite set is a set which is not finite. It is not possible to explicitly list out of all the elements of an infinite set.
How many books are there in your bag? Can you count them? There may be 5, 7, or perhaps as many as 12 books. It means that the set of books in your bag has a limited number of elements. We can observe that many things around us exist in the form of sets. For example, in your class, there are sets of tables, sets of chairs, sets of books, etc. The number of elements in these sets can all be easily counted. However, do all sets have elements that can be counted? Consider these two sets. Can you count the number of elements in them? In the set of fruits, there are 5 elements. Such sets, like the set of books in the bag, contain elements that are countable. They are called finite sets. Can you count the number of stars in the other set? We cannot count the number of stars. Such sets, whose elements are uncountable, are called infinite sets. Let's take a look at other examples. We have set A and set B. Set A contains vowels of the English alphabet. Set B contains the numbers 1, 2, 3 to 8. On counting, we see that set A contains 5 elements and set B contains 8 elements. Therefore, both are finite sets because the number of elements are countable. Here, we have a set of natural numbers. Recall that the set of natural numbers contain the numbers 1, 2, 3, 4, and so on. In tabular form, we write this set as. Observe that the number of elements in this set cannot be counted. Here, the dotted lines show that the set has infinite elements. Therefore, this set is an infinite set. Now let's test ourselves. Consider these two sets. For each set, determine if it is finite or infinite. Take a few moments to think and discuss. Let us review. Can we count all the people in Pakistan? Definitely, we can, but it is not an easy task. In fact, our government conducted the census in 2017 in all parts of Pakistan. So this is a finite set. In the set of even numbers, the elements start from 2, 4, 6, and go on indefinitely. In other words, the number of elements is not finite. Therefore, this is an infinite set. In this video, we learned that sets are either finite or infinite. Finite sets are those whose elements are countable, and infinite sets are those whose elements are uncountable.
The empty set or null set. Empty set or a null set. A set that does not contain any element is called an empty set or a null set. An empty set is denoted using this symbol, open or close bracket, or this crash 0. It is read as phi. What is an empty set? Empty sets are used to simplify the calculation and are must offer use while classifying all the odd items or those items that are considered to be rare. Definition of empty sets. A set can be defined as an empty set or a null set if it doesn't contain any elements. In set theory, an empty set may be used to classify a whole number between 6 and 7. Since this example does not have any definite answer, it can be represented using an empty set or a null set. We will consider the set of prime number as A. Thus A is equal to open 2, 3, 5, 7, 11, 13, 17, and so on and so far. Close parenthesis. Since there are no prime numbers between 14 and 16, we can conclude that X is an empty set. Another example. X is a natural number. 3 will be a null set because there is no natural number between number 9 and 10. How to represent an empty set? First, the notation of this empty set is A equal to open and close bracket. Second one, the same empty set A can also represented using the following notation. Empty set or X is equal to open or close bracket. The third one, we can use the special symbol of phi to represent an empty set. Take note that phi is a subset of every set, not an element of every set. And that's all. Thank you.
Hey everybody, this is Paul. Welcome to lesson 27 in the Intermediate Algebra series. So this is going to be a short tutorial, and I'm going to be discussing the empty set, otherwise known as the null set. So it's a really simple concept, and it basically looks like this. You just have an opening curly brace and a closing curly brace, and inside of your set you don't have any elements. And basically we can rewrite this as a 0 with a dash through it. So you're probably thinking, why do we even take the time to point this out? Well, sometimes when we're taking the intersection of two sets, for example, we might have this as our answer, so I just wanted to point it out to you so that you know what it means. So let's just do a really quick example so that the point sinks in here. Let's say that we have some set A, and A contains the elements 1, 3, 5, and 7. And then we have some set B, and we'll just say that B contains the elements 2, 4, 6, and 8. So let's say that we were asked to find the intersection of A and B. So now remember the intersection, we're comparing all the elements in A, and we're comparing them with all the elements in B, and any elements that exist in both A and B we write inside of our set that's denoted by the intersection A and B. So it turns out that none of the elements in A exist in B, and none of the elements in B exist in the set A. So it turns out that there's nothing in common, so we simply write just some brackets with nothing in them, or we just write this 0 with the slash. So basically this tells us that we've compared all of the elements in A with all of the elements in B, and that set A and set B have no elements in common. So it's a really simple concept, but I thought it would be important to let you guys know about this so that you knew what this meant if you saw it in any of your classes. So anyway, stay tuned for some more lessons in the Intermediate Algebra series. You guys have a great day, and if you haven't already, don't forget to subscribe.
Set equality. When one or more sets contains exactly the same number of members or elements, and also the order in which the members appear in the sets is not important.
Hello, I'm Professor von Schmohawk, and welcome to YU. In the previous lecture, we saw how to define sets and their members through the use of set builder notation. In this lecture, we will learn about several types of relations between sets. One such relation is equality. If two sets contain exactly the same elements, they are said to be equal. For example, set A, which consists of the elements 1, 2, and 3, and set B, consisting of the elements 2, 3, and 1, are equal, since they both contain the same elements. Notice that it doesn't matter that their elements are listed in different orders. This is because the order in which the elements of a set are listed is irrelevant. The set consisting of 1, 2, and 3 is exactly the same as the set consisting of 2, 3, and 1. The list does not imply that there is any particular order to the elements. It only says that every element listed is a member of the set. So if sets A and B contain the same elements, then they are equal. Another important relation between sets is the relation of subset. If all the elements of set A are also contained in set B, then we say that set A is a subset of set B. This relation is denoted using the subset symbol. If two sets, A and B, are equal, then they are subsets of each other. This is because all the elements of A are members of B, and all the elements of B are also members of A. So any two sets that are equal are subsets of each other. And since every set is equal to itself, every set is also a subset of itself. So the subset symbol can be used whenever all the elements of A are also members of B, whether A has the same number of elements as B or has fewer elements. But when A has fewer elements, we can be more specific and call A a proper subset of B. We denote this using the proper subset symbol, which is the subset symbol without the line underneath. In addition to the relation of subset, a set can also be a superset. In any case where set A is a subset of set B, we can also say that set B is a superset of set A. This relation is denoted using the superset symbol, which is the subset symbol reversed. Likewise, if A is a proper subset of B, then B is a proper superset of A. But what about the empty set? The set containing no elements. The empty set is considered to be a subset of every other set, including itself. In fact, the empty set is the only set which is a subset of every set. So far, we have represented sets by listing their members, or using set builder notation, or by drawing little ovals with the elements inside. In the next lecture, we will see how to visualize sets using Venn diagrams.
What is a universal set? The universe is something that pretty much contains everything you can think of. So does that mean the universal set is a set that contains everything? Yes, it does, but it should be suitable. But what is suitable? Look at these three sets. Set A, which is a set of all x such that x is a student of class 5A. This set will have all students of class 5A as its elements. Similarly, let's set B, which is a set of all x such that x is a student of class 5B. And set C, which is a set of all x such that x is a student of class 5C. We assume there are just 3 divisions of class 5. What do you think will be the universal set here? It's denoted by capital U. The universal set in this case would be the set of all x such that x is a student of class 5. This is where it gets interesting. You could have said that the universal set is a set of all students in your school or set of all students in the world. But that would not be correct. The set of all students of class 5 is more suitable. It means that U is like the main set and A, B and C are parts of it. Every student of class 5A will surely be a part of the set of students of class 5. In mathematical terms, we can say that set A is a proper subset of the universal set. Remember, for A to be a proper subset of U, there has to be at least one element in U that is not present in A. Similarly, sets B and C are also proper subsets of the universal set. So all the sets under consideration should be proper subsets of the universal set. Here is another example. Consider the segment AB, which looks like this. It has 2 points in between, point P and point Q. Just like the previous example, consider 3 sets here. Let set D be the set of all x such that x is a point on segment AP. This set will contain every point that lies here in this range. Let E be a set of all x such that x is a point on the segment PQ, which is this region. And let F be the set of all x such that x is a point on segment QB. Now try and think of the universal set in this case. It's simple. It will be this entire segment AB. The universal set will be the set of all x such that x is a point on segment AB. And remember, every set under consideration will be a proper subset of the universal set.
My name is Berjan Tenido from BSIT 1B. My topic is all about complement of the intersections of sets. The complement of the set X intersection of sets Y is the set of elements that are members of the universal set. Union of sets but not members of X, U, and Y. It is denoted by X intersection of two sets Y. Examples: suppose U equals set of positive integers less than 10, X equals 1, 2, 5, 6, 7, and Y equals 1, 3, 4, 5, 6, 8. A. Draw a Venn diagram to illustrate X intersection of two sets Y. B. Find X union of two sets. Then solution. First, fill in the elements for X intersection of two sets Y equals 1, 5, 6. Fill in the other elements for X and Y and for U. Shade the region outside and X intersection of two sets Y to indicate X union of two sets Y.
My name is Judith Biasis from BSIT 1B.
This is my topic. Binular diagram is a picture that presents it under relationship. Containment is a closed curve, the elements of which represented by the interior of the curve. The relationship to be represented are overlap, containment of either.
Now let's say if we have set A, which contain the elements 2, 4, 5, 6, and 9. And we also have set B, which contain the elements 2, 3, 5, 6, 7, 9, and 10. So what is the intersection of set A and B? How can we get the answer? To find the intersection, we need to find out which elements are common to both sets. So both sets contain a 2, they contain a 5, a 6, and also a 9. So therefore, the intersection of sets A and B is 2, 3, actually not 3, but 2, 5, 6, and 9. And that's it. So that's how you could find the intersection of two sets. So now let's work on some more examples. You can pause the video and try this one if you want to. Let me use some different letters. So let's say this is set C, and it contains the elements 3, 4, 6, 7, and 10. And also set D, which contain the elements 3, 6, 8, and 9. So feel free to pause the video and determine the intersection of sets C and D. Go ahead and try it. So which elements are common to both sets? So 3 is common to both sets, 6, and that's it. So for this particular example, it's only 3 and 6. So that's the intersection of the two sets. So this is the answer. Let's try another example. Let's say set F contains the elements A, B, C, D, F, G, and J. And set G contains the elements A, C, G, H, and K. So what is the intersection between sets F and G? So feel free to take a minute and try it. So let's see which elements are shared between both sets. So both sets contain element A, element C, G, and that is it. So the intersection of F and G is going to be A, C, and G. So as you can see, finding the intersection is pretty straightforward. But now what about this particular example? Let's say set J contains the elements 5, 7, 10, and 11. And set K has the elements 2, 4, 8, and 13. What is the intersection of J and K? Now notice that there is no common element shared between the two sets. The elements in J are completely different from the elements in K. So in that case, the intersection of J and K is going to be empty. There's going to be nothing inside. So if there's nothing inside, if you have an empty set, you have a null set. So this is the answer. You have to use a Greek symbol phi. Now let's say we have set R, which contains the numbers 3, 4, 7, and 10, and set S, which is basically an empty set. What is the intersection of R and S? The intersection of a set with numbers and an empty set is going to be another empty set or a null set. So that's it for this one. Now let's focus on the second type of problem that we need to talk about, and that is to find the union of two sets. So let's say that set A contains the elements 1, 2, 3, and 4. And set B contains the elements 3, 4, 5, and 6. So what is the union of these two sets? When I think of union, I think of combining these into a larger set. Now notice that we do have some common numbers, 3 and 4. Now the union will contain everything in both sets, but 3 and 4, we're not going to write it twice, only once. So the union of set A and B is going to be 1, 2, 3, 4, 5, and 6. So we're going to write everything in both sets, but only write it once. So let's try some other examples. So let's say set C is 3, 5, 9, 11, and 13. And set D is 2, 3, 6, 8, and 12. Go ahead and find a union between sets C and D. Go ahead and try that. So all we got to do is just write all the numbers in C and D. So let's put it in ascending order. So we have a 2, a 3, there's a 5, a 6, there's no 7. So we have an 8, a 9, there's no 10, but we have an 11, 12, and 13. And so that's it. So that's the union of those two sets. Here's another example. Let's say that set J contains the letters A, C, D, and E, and that set K contains the letters A, B, F, E, and G. Go ahead and determine the union between J and K. So just like before, all we need to do is write all the letters. So we have an A, a B, C, D, E, F, and G. And that's it for that question. Let's say that set X contains the numbers 2, 5, 8, 12. And set Y, let's say, is an empty set. What is the union of a set with numbers and an empty set? Well, the empty set is not going to add anything. It's like saying 15 plus 0, that's going to be 15. So therefore, the union of set X with an empty set Y is going to be the same as set X. It's 2, 5, 8, and 12. It's not going to change. But the intersection of a set with something and a set with nothing, it's going to be an empty set. So just something to keep in mind. Now, here's a question for you. Let's say if set A contains the numbers 3, 4, 5, and 7, and set B contains the numbers 2, 4, 5, and 8. How can you determine the intersection of A and B and a union of A and B and represent the results using a Venn diagram? So circle A and circle B in its separated form. Set A contains the numbers 3, 4, 5, and 7. B contains the numbers 2, 4, 5, and 8. Now, the intersection of these two, I'm running out of space here, is 4 and 5. 4 and 5 are found in both. But to represent that using Venn diagrams, what we need to do is put the two circles together and draw it this way. So this is set A and set B. So in the middle is the intersection of A and B, which contains these elements, 4 and 5. Now A also contains 3 and 7, and B also contains 2 and 8. But 4 and 5 is common to A and B, so we put that in the middle. Now the union of these two sets is basically everything. It contains the numbers 2, 3, 4, 5, 7, and 8. And I'm running out of space. So this entire system with the two circles represents the union of A and B because it contains all the numbers 2, 3, 4, 5, 7, and 8. But the intersection is limited by this region here because it only contains the elements common to both sets. So hopefully this helps you to see the relationship between intersection of sets and union of sets as it relates to Venn diagrams. So that's it for this video. Thanks for watching and have a good day.